So in this video, we're going to go over all of the reactions for acid chlorides. So this is chapter 20 if you're going by the Wiley Plus textbook. And we're just going to go over the mechanism and every single reaction that you got to know. So for the first one, we're going to know how to prepare acid chlorides. So here we're going to treat a carboxylic acid with SOCl2, and this will give you the following acid chloride. Now for the mechanism for the preparation of the acyl halide, one of these bonds from the double bond to oxygen come in and attack the sulfur, which is then going to make this double bond fall onto the oxygen, giving you this as the product. And then from here, you can have this lone pair fall onto that bond, giving you this. Okay, and then from here, you're going to have the negative charged oxygen have a lone pair fall in and create a double bond, which is going to cause the chlorine group to kick off because it's a good leaving group. And then that same chlorine atom is going to come in and take that hydrogen, making this bond fall back onto the oxygen. Okay. And now from here, we created a good leaving group with the sulfur atom attached to the oxygen. Another chlorine atom come in and that, and then it's going to make the bond fall onto the oxygen, giving you this. Now again, this is a very good leaving group, so a lone pair from the negatively charged oxygen is going to go ahead and fall down on here, and then it's going to kick off that, giving you this as your product. That was drawn very awkwardly. This is a better way to represent it. But yeah, that's how you prepare a acid chloride. Okay, so I've created a general summary of all the reactions that you need to know that happen with acid chlorides. And we're going to be going over every single one in this video with the mechanism, and we're going to start with how to prepare an ester. You can have acidic conditions, basic conditions, and neutral conditions. I'm going to show you how to do the neutral conditions, but if you have an acidic condition, it's going to begin with a proton transfer protonating the carbonyl group, and with a basic condition, it can just start with a nucleophilic attack. A lot of this is very similar to the aldehydes and ketones chapter, where we learn how to protonate and under acidic conditions and just do nucleophilic attacks under basic conditions. So I'm just going to show you how to do the neutral way, which depending on your professor, you'll see whichever one of these that I just mentioned. So to begin with, we're going to have a nucleophilic attack right there, and it's going to make the double bond fall into the oxygen, give you this. Okay, now from here, you're going to have another ROH group come in, or pyridine, whichever one is going to come in and deprotonate the hydrogen atom right here. I'm just going to do another ROH group, and it's going to make that bond fall into oxygen. Forgot to draw the chlorine. And from here, you're going to have a OR group and a negatively charged oxygen atom. From here, one of the lone pairs can go ahead and fall on to that bond, kicking off the chlorine because chlorine's a good leaving group, giving you the resulting product of an ester. So this one's pretty straightforward. If you want to make an ester, the reagents is more than likely just going to be an OR group, whatever you need, an ethyl, a methyl group attached to the oxygen, but pretty simple. For the next reaction, we're going to create a amide. So amides are very basic, so you can go ahead and just start with a nucleophilic attack. It's going to be positively charged. Okay, and from here you can have another ammonia group come in and deprotonate one of the hydrogens. From here, the lone pair is going to go ahead and fall down, and the chlorine is going to get kicked off. And there you go, that's how you make an amide. It's a very simple mechanism, not too complicated. And we're going to move on to the next one. Okay, for the reduction of a acid chloride, and we're going to treat it with lithium aluminum hydride, the first step that's going to happen is that you're going to have a hydrogen attached to the aluminum H3. This hydrogen bond is going to go ahead and come in and do a attack on the carbonyl group, giving you this and that new hydrogen right there. Okay, and then from here you're going to have a lone pair go ahead and fall down onto that bond, kicking off the chlorine group, giving you this. And we use excess, so the same thing is going to happen. You're going to have another hydrogen to the AlH3. It's going to come in and attack, giving you another hydrogen. And from here, this is where the acidic workup step comes in, where you're going to have hydronium lose a hydrogen to that oxygen atom, and that's going to give you this. So this one's pretty easy too. Okay, for this one, this is under the organometallic section, and we're going to be treating with a Grignard reagent. So from here, I'm just going to write the CH3MgBr as a negatively charged carbon atom, so he's going to come in and attack there. And from here, a lone pair is going to go ahead and fall down, kicking off the chlorine. And then the same reaction is going to happen. You're going to have another carbon atom come in and attack, giving you this. And then from here, the acid workup step is going to occur, where a lone pair comes in and grabs that hydrogen atom, and it's going to give you that as the product. So pretty straightforward again, very similar to the reduction with lithium aluminum hydride, except for this time we're adding on carbon atoms. Okay, for our next one. Okay, so this reagent is very similar to the Grignard reagent, except that it stops at the ketone. Now, that's really the only difference between the Grignard and this reagent. It undergoes a similar mechanism too. You're just going to have a CH3 group come in and attack. And then a lone pair is going to go ahead and collapse and kick off the chlorine group, giving you the ketone. This one's very easy. All you gotta know is that it just stops at the ketone. All right, and that should be it for acid chlorides.